Welcome back, Gen Chem students. Today we are going to be focusing on equilibrium and something called Le Chatelier's principle. So let's go ahead and get started. How does equilibrium work in a chemical reaction? It works with something called reversible reactions. This is a new idea that we have not looked at before. A reversible reaction we can see is occurring because of this double-sided arrow that you see there. So the reaction can go both directions. A reversible reaction is one in which the conversion of reactants to products and the conversion of products to reactants occur at the same time. So in this reaction that we see here, we have nitrogen and hydrogen gas combining to form ammonia, which is the NH3, and we also have ammonia decomposing or breaking down to form nitrogen and hydrogen gas. In the forward reaction, which is the traditional way of looking at a reaction, hydrogen and nitrogen are combining to form the product of ammonia. In the reverse reaction, ammonia is decomposing into the products of hydrogen and nitrogen. Now, in the very beginning of the reaction, we have a lot of nitrogen and hydrogen, and we don't have any ammonia. But as that reaction proceeds, the rate of the forward reaction continues to decrease, and the rate of the reverse reaction continues to increase until the two rates are equal and their concentrations become constant. That's what this graph here is showing us. So in the very beginning, we have a lot of nitrogen and hydrogen, and we have zero ammonia. We haven't made any product yet. Now, nitrogen and hydrogen react to make the ammonia. And as they're reacting to make ammonia, the ammonia concentration is increasing. And eventually that ammonia is going to start breaking down and making hydrogen and nitrogen. And their rates become constant. So that is what equilibrium is. When the rate of the forward reaction and the rate of the reverse reaction become equal, and we have this constant concentration occurring. All right, so equilibrium, its official definition is when the forward and reverse rates of a reversible reaction are equal. This is represented with that double-sided arrow in the reaction, like we saw. The concentration of the reactants in the products become constant. And we can see this with something like constant color or constant pressure. When we look at our lab and our pre-lab, we'll see examples of that. Constant concentration does not mean equal. So when we look at this graph again, we see that these lines are not equal. If they were equal, they'd all be on top of each other and converge into the same line. We have constant concentration, but not equal concentration. Now, in order for equilibrium to occur, three things must be true. We must have a closed container. We must have constant temperature and pressure. And we must have a reversible reaction. Okay, so we have to have those three conditions to be true for equilibrium to occur. Now we're going to look at one of the factors that deals with equilibrium, and that is called Le Chatelier's principle. Le Chatelier's principle states that if a system at equilibrium is stressed, the equilibrium will shift until the stress is relieved. And a stress is considered anything that changes the forward or the reverse rate. So we're going to talk about what these shifts look like. Now, a shift to the right, so if we're moving to the right side of the reaction, we are moving to the product side. Okay. So right side of the reaction is meaning the product side of the reaction. So a shift to the right means the forward reaction was favored and the product concentration will end up increasing and the reactant concentration decreases when our equilibrium is reestablished. A shift to the left, so when we're talking about the left side, we are talking about the side of the reactants. So a shift to the left means a reverse reaction was favored, and the reactants concentration now will increase. And the product's concentration decreases when the equilibrium is reestablished. So there are 3 stresses that affect equilibrium. One of them is manipulating concentration. So the statement here says, increasing the concentration on one side of an equation shifts equilibrium towards the opposite side. So if I increase a substance concentration, it's going to shift to the opposite direction. That's a really, really, really important concept. So adding a reactant will push equilibrium to the right side. If I decrease a reactant, and the opposite's going to occur. If I pull a reactant away, the reaction is going to want to make up for that and increase the amount of reactant. So it's going to pull the equilibrium to the left-hand side. Now, if I add a product, it's going to push it to the opposite direction. It's going to push equilibrium to the left. And if I remove a product, it's going to want to make up for that, and it's going to pull equilibrium to the same side. So it's going to pull it to the right-hand side of the reaction. So let's look together at what I'm talking about here. So our first stress is to add carbon monoxide. If I increase the concentration of carbon monoxide, it's going to push equilibrium to the opposite direction. And that would push it then to the right-hand side of the reaction. If I increase methane, which is CH4, that means now I'm increasing this substance. It's going to push it to the opposite direction. If you increase something, it pushes it to the opposite side. So it's going to push it to the left-hand side. Now, the next concept is removing hydrogen. If I take away a substance, it's going to pull it and keep it on the same side. So by removing hydrogen, it's going to pull it and keep it on the left-hand side of the reaction. And if I decrease water, it's going to pull it again to the same side. It's going to pull it to the right-hand side of the equation. All right, now the next idea that we're looking at is the effect on product concentrations. Your products are on the right-hand side of the reaction. Therefore, anytime you go to the right, product concentration will increase. So when you see right, it's going to be an increase in product concentration. Anytime you go to the left, you're moving away from products. Therefore, your product concentration will decrease. So both left-hand shifts will be decreased. It's much easier to figure out that final column after you've determined your shifts. All right, the next stress that affects equilibrium is temperature. Temperature states that increasing temperature is going to favor the endothermic direction. Now that's all good and great as long as you know what the endothermic direction is. It's much easier if we treat it like a concentration with the push and pull idea. So we're going to look at temperature as a matter of energy. How we're affecting temperature is how we're affecting energy. Remember, temperature is a measure of the average kinetic energy of a system. So temperature and energy go hand in hand. They're essentially the same thing. Now, we represent energy with this triangle H. This triangle H stands for change in energy. When your change in energy or enthalpy is negative, that means our reaction is exothermic. Okay, we're releasing energy and giving it off. So energy is going to be on the right-hand side. Remember, an exothermic reaction is releasing energy. So energy is going to be on the right-hand side. When our delta H value here is positive, so our change in energy is positive, that means we have an endothermic reaction. Energy is being absorbed into the reaction, and energy is going to be written on the left-hand side. This is such an important idea. This is something that you're going to come back to over and over again as we're doing our work with Le Chatelier's principle. So the first question we see here is rewrite the equation with energy. Notice that our change in enthalpy, our change in energy value is negative. Well, up here we said when our change in energy is negative, we have an exothermic reaction and energy is going to be written on the right-hand side. So I'm going to write energy on the right-hand side there. And I'm also going to go with a different color here. All right, so the first stress we're looking at is increasing temperature. If I'm increasing temperature, that means I'm increasing my energy. If I increase something, we said it's going to push it to the opposite direction. So that's going to push it to the left side of the reaction. Now, if we remove something, that's always going to pull it to the same side of the reaction. So if I remove energy, it's going to pull it to the same side. It's going to pull it to the right side of the reaction. And again, if I add thermal energy, if I add something, it's going to push the reaction to the opposite side. So adding thermal energy is the same as adding energy. The reaction is going to push to the opposite side, which is the left-hand side. Now my reactants are on the left-hand side. So whenever I shift to the left, my reactant concentration is going to increase. So anytime I see left, it's going to be increase. Anytime I move to the right side, I'm moving away from the reactants, so that is going to be a decrease in reactant concentration. The last stress that we have for Le Chatelier's principle is dealing with pressure and volume. Now remember, Boyle's law stated that pressure and volume are inverse. So that means if one goes up, the other's going to go down. That's going to have an effect on what we're looking at here. So increasing pressure, which is the same as decreasing volume. Okay, they're inversely proportional to each other. So if I increase the pressure of the system, it's going to favor the side of the reaction with fewer gas particles. And the reason is if you increase pressure, the system is going to shift to make that pressure go back down. Well, if it goes to the side with fewer gas particles, you're going to have fewer collisions, which will eventually lower the gas pressure. Now, decreasing pressure, which is the same as increasing volume, is going to favor the side with more gas particles. If I decrease pressure, the system is going to want to relieve that stress and make the pressure go back up. It does that by going to the side with more gas particles because you're going to have more collisions, and that's going to make the pressure increase. So anytime you have a pressure problem, it is essential that you write down the number of gas particles on each side of the reaction. The way we do that is we start off by looking at our states of matter. Here we have gas, 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 gas. So everything counts as a gas particle. Then we add up our coefficients. I have no coefficient in front of carbon monoxide, so that's like an understood 1. I'm going to add that to the 3 here. 1 plus 3 gives me a total of 4 gas particles on my reactant side. In front of methane, I have no coefficient, so that's like an understood 1. In front of water, I have no coefficient, so that's like an understood 1. So 1 plus 1 adds up to 2. On my product side, I have 2 gas particles. So if I increase pressure for the first stress, it says that we're going to go to the side with fewer gas particles. I have fewer gas particles on the right-hand side of this reaction. Decreasing volume. Whenever you see volume, change it to what it's doing to pressure. A decrease in volume is going to do the opposite to pressure, which means it's increasing your pressure. Well, we just said an increase in pressure is going to favor the side with fewer gas particles, which is going to be the right-hand side of the reaction. An increase in volume is going to do the opposite to pressure. It's going to decrease pressure. Well, a decrease in pressure is going to favor the side with more gas particles. We have more gas particles on the left-hand side of the reaction, so that's going to be to the left. Let's change colors here. All right, so then our next column is the effect on carbon monoxide. Whenever I give you a substance like this, don't focus on the substance, write down which side of the reaction it is. Carbon monoxide is on the left-hand side of the reaction, so it's a reactant. Anytime then you go to the left-hand side, that means our reactants will increase because you're going to the same side. Anytime you go to the right side, you're moving away from the reactants, so that concentration will decrease. So both right shifts are decrease and decrease. All right, we're going to do a couple more problems here with pressure. Again, we start with a number of gas particles. Look at your states of matter. We have a gas, here we have a solid, don't count that. Gas and gas. On our left-hand side, then we have 1 gas particle. On our product side, we have 1 plus 1 for a total of 2 gas particles. If I increase pressure, it's going to favor the side with fewer gas particles. We have fewer gas particles on our reactant side or left-hand side. Whenever you see volume, it does the opposite to pressure. So it means it is decreasing pressure. A decrease in pressure is going to favor the side with more gas particles. We have more gas particles on the right-hand side of the reaction. Products. So what is our effect on product concentration? Products are on the right-hand side of the reaction. Anytime we go to the right, then it's going to be an increase in concentration. Anytime we go to the left, we're moving away from it, so it's going to be a decrease in concentration. Our last reaction here that we're going to look at, again, we're going to start by counting our number of gas particles. Here on the left-hand side, I have a gas and a gas, so I'm going to count both of those. Coefficients are 1 plus 1 for a total of 2 gas particles. On the right-hand side, it's also a gas particle, and here the coefficient is 2. So I have 2 gas particles. Notice these are the same. Now I don't have fewer or more gas particles, which means my pressure and volume are going to have no effect on equilibrium. So I would write everything as no change, no change. So anytime you have the same number of gas particles on both sides of the reaction, it is going to be no change to the shift and the effect on product or reactant concentration. All right, a couple more ideas that we have to look at with Le Chatelier's principle. A catalyst speeds up both directions of for the forward and the reverse direction. Therefore, it has no effect on equilibrium. So whenever you see a problem where it says add a catalyst, it's going to be a no change for Le Chatelier's problems. All right, the other idea. Only gases and aqueous substances have variable concentration. Remember, concentration is moles of solute divided by liters of solution. Well, a solid, if it's a pure solid, is not dissolved in liters of solution. So it has a constant concentration. And if you have a liquid and it's a pure liquid, again, it's not dissolved in another liquid. So it does not have variable concentration. So what this means is only gases and aqueous substances are counted for shifts or stresses in Le Chatelier's problems. Solids and liquids are not. So anytime you see a solid, a liquid, or a catalyst, those answers are all going to be no change for your equilibrium problems. Now, next week, we're going to do a Le Chatelier's class worksheet together, and we'll see examples of those types of problems together. And we'll do that before I assign you the homework. And that is it for Chapter 18 notes.